This is one of the more foundational concepts of number theory, this and prime factorization. So you'll want to kind of stay a bit tight on this one. Do everything I'm doing so you can kind of digest it as we go, keep active engagement. Now, a major thing I want you to keep in mind as we go is just simple idea of a loop or a cycle or a circle, right? How things start at one position, go around, and return to where they started. That's one of the big things. The second is this term we're going to introduce, which is congruency. And you might have seen this in geometry. All this says is that a number A is congruent to a number B if, when you take A and you divide them by the same number K, they have the same remainder. In this case, I don't know, I would say remainder 2 on this side, remainder 2 on this side. They both have a remainder of 2, then they're congruent. This will make a little bit more sense with an actual example. Let's take 12 divided by 5. We'll take 17, divide that by 5. 5 goes into 12 two times for 10. 12 minus 10, remainder of 2. 5 goes into 17 three times, 15. 17 minus 15, remainder of 2. So the 12 and 17, just by being pretty different, one's prime and one's not, you might not think they really share anything in common, but it turns out when divided by 15, these two are actually congruent. And there's a shorthand for this notation, which is just A mod B, where the number that's being divided by B is at the beginning. So if we had the 12 being modded by 5, then 12 would go where A is, 5 would go where B is. That's all it's saying. Just 12 divided by 5 really is when you see mod, just kind of think of division and remainders. And so again, if two numbers have the same remainder and they're divided by a number, they are said to be congruent. And you might be wondering about where's the power in that, and it'll kind of become evident as we go along. Okay, and so we'll go ahead and do two problems really quick. They're pretty easy. We'll kind of show this applied to a bit of larger values. So we'll do 4583 mod 4. First thing you're going to want to do is expand this out like we did with base in the number bases video. 5 10 second plus 8 times 10 to the 1 plus 3. And so one interesting thing you can note here is that congruency, or rather multiplication and raising things to the powers of, will actually preserve congruency through the operation, right? So if we have 12 squared and it's equal to, 7 squared, by some mod, squaring them actually won't affect the congruency. And that of course applies to higher powers as well. It's just kind of the cyclical nature of multiplication when powers are involved. So you can kind of think of, the exponents, or rather the powers of something going in cycles in terms of congruency. So what all that really means is when we look at, a base raised to a power, we can attack the base to make it easier to work with instead of the power. The power will still encode some information, but at least for this purpose right here that we're dealing with, we don't really need all of that. We just want to make this easy to work with, right? So that's all we're doing. We're just making this number 10 to the third easy to work with. Instead of 1,000, we want to work with something as small as we can make it. So all we do is apply the mod operation to it. So we take 10 mod 4, and that'll behave in terms of the remainder the same as if we do 10 divided by 4, we get a remainder of 2, right? So we get 2 mod 4. Because 4 goes into 10 two times. 10 minus 8 is 2. So that means we turn all of these 10s into 2s, which you can see would drastically shrink the number. We go from 10 to the third, which is 1,000, to 2 to the third, which is 8. So 4 times 8 plus 5 times 4 plus 8 times 2 plus 3, we get 32, plus 20, plus 16, plus 3 equals 52 plus 16. Yeah, should be 71. So that just means this is congruent to 71 mod 4. And obviously you can go even further, keep modding it down, but this is the smallest one that we can do with this operation. That is still congruent to this. Let's do one more. Let's do mod 9. And again, same idea. Should be able to do it pretty fast by now. Eventually get to the point where you can do all this in your head. Still just doing it just so you can see the thought process behind it. And again, we just mod the base. That would be equal to a remainder of 1. So that's congruent to 1 mod 9. So now we can replace these with 1. And we know that powers don't affect the 1. Excuse me. So it's really just each digit added to themselves. 13 plus 3, 16, 17. 17 mod 9. And you'll notice all sorts of patterns. With modding, you'll see certain numbers come up quite a lot.